When we consider equilibrium constants, we have a number of factors to worry about, as always. But primarily, it's not terribly difficult to come up with the equilibrium expression for a particular reaction. If we say that all of these are gases, this is going to make it a little bit easier on us. The equilibrium expression is always going to be having our equilibrium constant equal to the products over the reactants. And for this generic equation, which we've used before, we'll see that it will be the concentration of C raised to the C power, right, if that's our coefficient, times D to the D power over A to the A power and B to the B power. So our products and over our reactants. All of these components raised to the power of their coefficient. So that's why we saw in the previous example we had 3H2 and nitrogen turning into 2 ammonias. We had ammonia squared on top, hydrogen cubed times nitrogen on the bottom. And so that would be our equilibrium constant. And remember, again, this is our equilibrium expression here. And so we're going to see that we can utilize equilibrium constants. We'll see that in our next video, how to actually work with them. But we'll just talk about all the different types of equilibrium constants and how to combine them together, how to mess with them if we were so inclined. And so with this, we could say, what if we want to think about the reaction in reverse? Perhaps not too bad. If we think about instead, CC plus DD turns into AA plus BB. Well, our new equilibrium expression would be simply the inverse of our previous one. It simply depends which way we're looking at this reaction. Whichever set we decide to call reactants, whichever set we decide to call products, it doesn't matter. We'll have a different Kc. And I'm going to just say this is Kc1 and Kc2. This is reaction 2, this is reaction 1. They're the same reaction, but in reverse. So focusing on the reverse reaction here. We're going to get A to the A power, B to the B power, C to the C power, and D to the D power. And if we compare with Kc1, we see that it's the inverse of it. And if we look at the second Kc, it's the opposite, right? So our first kind of thing with working with Kc, we'll see later on all these will work for Kp as well. For a reverse reaction, the K of the reverse, or forward, we can say, let's say reverse, why not? Will be 1 over Kc of the forward reaction. So it's just 1 over, it's the inverse. We flipped our fraction upside down. And so once we establish numerical values for these, we can actually work with them. And it's pretty simple. So let's say the Kc for a forward reaction is 0.001226, random number. The K for the reverse reaction would be 1 over 0.001226, which would be, here, let's actually do the math, 1 divided by 0.001226. We get 815.7, we'll say. So just the inverse number, whatever it happens to be. We'll again talk about math with the Kcs later on in our next video. But suffice it to say, if we're looking at a reaction, we want to reverse it, all we need to do is invert the K value for it. Okay. Hopefully not too bad. If, I'm going to simplify this, we'll make an easier reaction for us. If this is our original reaction, Well, we have Kc equals B times C over A. If we decide to increase all the coefficients, so say we want to double this reaction for whatever reason we want, we can do that. So let's say, what about 2A to 2B to 2C? Not a problem. For this, our new reaction would be B squared, C squared. I'm going to say again 1 and 2 just so we have something to compare. Oops, and I put my C outside. There we go. If we compare them, well, Kc2 is just, remember with squares, since they're all squared, we can raise the whole thing to the second power. And so, in this case, Kc2 is Kc1 squared. Whatever numerical value it was, squared. And so, again, this is how we can relate rate constants to each other. Because, as we'll see in our next example of what to do, remember with Hess's law, we could change the coefficients of a reaction if we needed things to cancel out properly. And then we saw we would multiply delta H by that, whatever we multiplied the equation by. For equilibrium constants, instead of just multiplying, we have to square or cube our process. And so, really, whatever your second reaction happens to be, whatever coefficients you're changing, you're just going to raise that to the n power. So if you go from A turns into B plus C, whatever reaction you're looking at, to adding coefficients, that's where this comes in. So your new equilibrium constant will be your original equilibrium constant raised to the n power. So that'll be our new one here. And finally, just like with Hess's law, remember that we could find delta H for an overall reaction by adding the delta H of individual steps. We can do the same thing here. If we want to say A turns into B plus C, and then B plus D turns into E, whatever it may be, we have 2 Kc's for these particular reactions, whatever they may be. When we combine these two, though, if we were to add these reactions together, we get A plus D turns into C plus E, apparently. And we get Kc3 for this particular overall reaction. Reaction 1, reaction 2, reaction 3. The Kc for the third reaction is the product of the first 2 Ks. So if you're going to be combining reactions together, you need to multiply their equilibrium constants to get your new equilibrium constant. So with Hess's law, remember, we added the enthalpies together. With equilibrium constants, we multiply them together. And remember, again, if you need to raise something to a power, then what you're going to need to do is square or cube that particular Kc and then carry it along. So just like before. We can take a look at an example. How about we look at, we did this one yesterday. CO2 plus NO. And for this process, we saw that we could have the following 2 steps. NO3 plus NO, and then we had NO3 plus CO turns into CO2 plus NO2. Right, and so if we add these two together, we saw that these two would cancel out, as well as the NO3s. We get our overall reaction again, if we add these together. But suffice it to say we had K equals 0.04. Again, I'm just making up numbers. And let's say Kc for this reaction was 22.4, whatever it may be. The K for this reaction would be the product of those two. And 0.004 times 22.4, whatever it is, 0.0896. That would be our Kc for the new reaction. So if you know Kcs for individual steps, you can multiply them together to get your product. If you need to reverse a reaction, you will do 1 over Kc. If you need to multiply a reaction by a coefficient, what you'll need to do is raise the Kc to whatever power that may be. So if you need to triple the coefficients of a reaction, you need to cube your Kc. And finally, we have Kp. This is an equilibrium constant for pressure instead. And when we're looking at Kp, if we take our same equation from before, everything's going to be a gas, right, for pressure. When we're taking a look at Kp, instead of looking at concentrations, we're looking at pressures. So we're looking at the pressure of the ammonia squared. We're looking at the pressure of nitrogen and the pressure of hydrogen cubed. So it's the same as concentration, but we're using different units, pressure units. And if you really want, you can go through the ideal gas law, have some fun with that, but we can relate the pressure Kp and Kc together. And if you want to mess that, you can see the derivation in the book, or you can accept it. We're going to see that you can relate Kp and Kc to each other for gases. The Kp for a reaction is Kc times RT to the delta N power. And delta N is the moles of gas in the products minus the moles of gas in the reactants. And so for this example, we have 2 moles of gas in the products, 4 moles of gas in the reactants. So delta N for this reaction is -2. We have 2 moles that are being produced from 4 moles. So if we want to convert between the two, if we have a numerical value for Kp or Kc, we can convert them using this relationship. So R is our gas constant, 0.08206. Liter atmosphere mole Kelvin. And then T, of course, is temp in Kelvin. And so you can use this equation to convert between Kp and Kc. And so that's not quite it. We have one more thing to note. With equilibrium constants, last note here, solids and liquids do not go into equilibrium expression. Because they don't have concentrations. They do not go into an equilibrium expression. So only aqueous and gases. And so if we take a look, let's say we've got H2O2, which is aqueous. That's breaking into water, which is a liquid, and oxygen, which is a gas. The equilibrium constant for this equation, we cannot include liquids in our equilibrium expression. So it's simply O2 over H2O2 squared. We do not include liquids or solids in our equilibrium expressions, only gases and aqueous things. So keep that in mind for next time. We'll take a look at how to use equilibrium constants in our next video.